Good morning. This lesson is for my Trig-Precalc class, but before I get started, I want to say I hope that everybody is doing all right out there. This is for chapter 4, lesson 5 or 4 or 6. I don't know what lesson it is. I'll just title it correctly in the title of the lesson. But anyways, let's go ahead and jump into our goals. We only have one goal with this lesson, and it's going to be using trig in real-world situations. And this situation is something that I actually experienced not that long ago. So you're aware that I'm building a garage and I needed to buy a ladder. And I had to make, and this ladder, I think it's DD, not TT. I don't know how to spell, let me fix that. I do think it's DDER. I needed to buy a ladder that met OSHA standards, and it would have a length of 3 feet more needed and have a 75-degree angle off the ground. So here's a crudely drawn picture of my garage project, 2-story. And this is supposed to be a ladder, and this ladder is supposed to sit 3 feet higher than the roof line, and it's supposed to make a 75-degree angle off the ground. Now, it needs to be 3 feet higher for safety issues. I don't know if you've ever climbed up a ladder and gotten onto a roof, but if the ladder stops at where the roof begins, you have to crawl up and lay flat and roll onto the roof. Now, if the ladder extends above the roof, you're actually climbing up the ladder higher than the roof, and to get on the roof, you just step off. It's a much safer way to get onto a roof, especially when that roof line is 21 feet off the ground. So I had to buy a ladder that met OSHA requirements, and I don't remember exactly what OSHA stands for, but it has to do with safety standards on construction sites. So this is a trig problem. This is a trig problem I had to do recently. So I had to make sure that I bought a ladder that was up to OSHA standards, meaning it would sit 3 feet higher than the roof line when it's making a 75-degree angle to the ground. So this literally is what we're doing. So I'm going to take what we have here and make a right triangle out of it. So we actually have something that looks like this. And if we figure out which trig ratio that is, so I have an angle, an opposite length, and a hypotenuse length, that means that I have a sine ratio problem. So I have sine of 75 degrees is equal to the opposite length divided by the hypotenuse length. And so we can solve this very quickly by multiplying both sides by x. The x's cancel out, and I'm now left with x times sine of 75, and that's equal to 21. Now remember, I got to get x by itself. Sine of 75 has a value. It's a y-coordinate somewhere on the unit circle. So I'm going to divide both sides by sine of 75. Now where is my calculator? Oh, there you are. So let me figure out what this is going to equal. So x is equal to 21 divided by sine of 75. Again, let me point out something to you. This y-coordinate is smaller than 1, bigger than 0. So I'm dividing by a small spoon, so my result will be larger. And that's going to make sense because the hypotenuse is the largest length on a right triangle. So it's 21 divided by sine of 75 and it's equal to 21.74. Alright, so X is equal to 21.74. I've never seen a ladder at a 3/4 of a foot long, so I'm going to round this up to 22. So X is equal to 22. Now remember, that length only gets us to here. We need to make sure that this length can be 3 feet longer. So for me to buy, or for me to get a ladder that's up to OSHA standards, it needs to be 25 foot. So I need a 25-foot ladder. I think it's DDR. Ladder. I really need to learn how to spell. I'm so bad at that. But that's not the end of this problem for me using trig. There's one more situation that arises that I need to know a number for. And if you look at the picture, it might not be so obvious. It might not be so obvious. I also need to know how far away from my building do I put the base of the ladder so I guarantee to have a 75-degree angle. Now, let me add a couple more dimensions to this problem. My eaves, which are the overhang of the roof, they actually are 3 feet in length, right? So they hang out 3 feet, which means that if I calculate this distance right here, and I add 3 feet to it, I know how far I need to put the base of the ladder away from my building so that I ensure that I have a 75-degree angle and my ladder will sit 3 feet above. So I thought that this would be a good lesson to see, because this is something that I did in my actual life that is using what I teach. So let's go ahead and find how far away the ladder needs to be placed. I have an angle, an opposite, and an adjacent, so I need to use tangent. So I have tangent of 75, and that's equal to 21 over y. Now, I just had a problem where the unknown was in the denominator, and I was able to just basically switch these locations and calculate it out and get a value. So I will switch the location, so y is equal to 21 divided by tangent of 75. So 21 divided by tangent of 75, and make sure your calculator's calculating in degrees. And the y value is 5.6 feet. Now remember, 5.6 feet is that length. I actually have to add another 3 feet away from the building in order to ensure that I have a 75-degree angle. So my distance of the base of the ladder needs to be a little bit more than 8.5 feet away. A little bit more than 8.5 feet away from the base of the building to ensure that I'm following the safety standard. And you want to follow the safety standards because it's very expensive to get sued. You know, that would be a terrible thing for me. And I mean, that even more terrible if someone got hurt. That would be more upsetting to me than the money. So anyways, again, this was just a lesson of showing you how I use trig in real life. I hope that this makes sense to you guys. I'm going to go ahead and end the lesson here. Have a good day, everybody. I'll see you later. Bye-bye.